Okay, well, let's go ahead and get started. So the topic for today is general linear models. What I want to cover today is just correlation, then look at simple linear models. Then we'll look at the more complex models, multivariable models. We want to look at the model validation, and then also talk a little bit about how we can account for nonlinear relationships or nonlinear functions with using linear models. So in terms of linear relationship between two variables, they're said to be correlated. So the data that we have is variables that are paired. So it can be the same person, the same patient, or they can be matched in some way. The variables obviously don't have to be measured on the same scale. So for example, height and weight, age and blood pressure. And so what we get with the correlation coefficient is the strength of relationship and then the direction of the relationship. And so in terms of numbers, the correlation coefficient can range from -1, where we have a perfect negative correlation, to a +1, where we would have a perfect positive correlation. And so what correlation tells you is the degree or the extent to which there's an ordered pairing of the values on one variable with the values of the other variable. And so if the correlation is positive, then what we have is the extent to which increasing values of one variable have the same order or rank as increasing values of the other variable. That doesn't mean that the values are the same necessarily or equal, but they have the same order. And if we have a negative correlation, then that's the extent to which increasing values of one variable have the same order as decreasing values of the other variable. So in terms of computations, basically the correlation coefficient is the standardized covariance between two variables. And we can look at the variance, which we'll label as or designate as S squared. And that's equal to the sum of the difference between each of the individual observed variables and the mean of all the variables divided by the sample size -1. And we can rewrite this as this observation minus the mean times the observation minus the mean. Sort of using this notation, then we can define the covariance as the sum of the difference between one variable's observations minus the mean of that variable times the observations of the other variable minus the mean of that variable. And so we call the two variables X and Y. And then the correlation is equal to this covariance divided by the product of the standard deviations of the two variables. And this is commonly known, or maybe not commonly known, but this is what is the Pearson product moment correlation. And so here's an example where we have a perfect positive correlation, and then on the right, a perfectly negative correlation, whereas one value is increasing, then in this case, the X variable, the Y variable is decreasing. So here's a couple of plots here that show no linear correlation. So in the first one, this is fairly obvious. Our correlation coefficient turns out to be 0.07. On the right-hand side, we can see that the correlation coefficient is virtually 0, but we can also see that even though there's no linear relationship, there is some kind of relationship, and in particular, a nonlinear relationship. And we'll talk about this a little bit later in the discussion. So when we talk about linear regression or ordinary least squares regression, what we're going to do is we're going to consider one of the variables as the dependent variable and the other as the independent variable, or the dependent variable is some outcome that we're interested in, and the independent variable is we want to determine whether there's some sort of relationship between that and the outcome or the dependent variable. And so we write this as y as a function of x. And so an example I'll give a little bit later, we're going to look at cholesterol as a function of age. And so what we say is we're going to regress y on x. Now we could also regress x on y, and that won't be the same. We won't get the same results unless we have perfect correlations, either positive or negative, between the two variables. So in linear regression, the dependent variable or the outcome is a continuous variable, and we assume that it's normally distributed. It has a normal distribution. And so we write our model as the outcome or the dependent variable is a function of beta sub 0, which we call the constant or the intercept term. And then we could have a number of independent variables, the x's, and then the betas are the regression coefficients associated with each variable. And so the regression coefficients in this case represent the change in the outcome or the dependent variable for every unit change in the independent variable or in the x. And in linear regression, the x's, the independent variables, they can be binary or they can be categorical or continuous. And then we typically write this equation with an epsilon at the end, and this represents our error variance, and I'll discuss what that is when we look at a specific example. So there's a couple of special cases of the general linear model. If we have one independent variable, and that independent variable is dichotomous, then we have just a simple t-test. And typically when we do that, we do what we call dummy code. We set one of the x's or one of the groups equal to 1 and the other one equal to 0. And if we do that, then the intercept or the beta sub 0 represents the value of y when x is equal to 0. If we have a multivariable linear regression and all of the x's, all of the independent variables are categorical, then we have what's known as analysis of variance. So there's a couple special cases of linear regression. So I want to illustrate what we mean when we're talking about linear regression. And so I have here some points that represented by the yellow circles that are for each individual, their age and their cholesterol value. And then the horizontal line across the middle, which we'll designate as capital Y, represents the overall mean of cholesterol values. And so in linear regression, what we are doing is we want to see if there's another variable or variables that explain the Y better than just the mean. Because if we had no other information and we wanted to know what was the most common value of Y, or what was the most common value of Y, we would say, well, it's just the mean. But if we add another variable in predicting the outcome, in this case cholesterol, what we're going to do is we're going to look at the observed values. That is, this is the actual value for an individual patient that represents his or her age and cholesterol level, and we'll designate that as little y sub I. And then our regression line, which I've already put in here, will designate as little y prime. And so that's the using age as a predictor of cholesterol. This is the regression line that we would get. And so what we want to do is we want to get the best fit line to represent the relationship between cholesterol and age. And we do that by minimizing the sum of the squared residuals between the observed and the predicted. And so we can look at it this way. If we have the difference between the observed and the mean, you see that we can split that up into two parts. We can split it up into the difference between the regression value, the y prime, and the mean. And then we can look at the difference between the observed and the regression line. And so if we do that, then we come up with this formula where the sum of all the squared differences between the observed value and the mean value then is equal to the sum of those two partitions, the y prime minus y, the mean, and then the y sub I minus the predicted value. And you see that these are all squared. If we didn't square them, we'd end up with a value of 0. And so what we want to do then, as I mentioned, we want to minimize the distance between the observed value and the predicted value, the regression value. And you can see that in my little example here that some are fairly large differences and some are fairly small. So in terms of our regressions here, we call the difference between the observed and the mean this. When we square that distance, we get the sum, what we call the total sum of squares, and that partitions into what we call the sum of squares regression, the difference between the regression value and the mean, and the sum of squares error, or we also term that a residual, the difference between the predicted value and the observed value. And so if we use our equation here, then we can see that the sum of squares, the total sum of squares is equal to the regression sum of squares plus the error sum of squares. And it turns out that probably the most important statistic for determining how good our regression is in fitting it to the data is to look at what's called the R squared. And the R squared is just the sum of squares regression divided by the total sum of squares, the regression plus the error. And so R squared then is interpreted as the difference or as the amount of variance in the outcome variable or the dependent variable that is explained by the independent variable. And it turns out if we take the square root of the R squared, we get the correlation coefficient or the absolute value of the correlation coefficient. We wouldn't know the direction until we actually plotted it and got the regression coefficient itself, whether it was positive or negative. So the R squared is basically how we evaluate how good our regression is as far as fitting to the actual data. And so the R squared will range between 0 and 1. And so obviously the higher the R squared value, the better the fit of the regression to the data. So let me give you an example here where I have some values of cholesterol and age. And so I'm going to regress cholesterol on age and look at the at this regression, see what we get. So in simple linear regression, where we have just one independent variable, as I mentioned, the b sub 0 or the beta sub 0 is the intercept, the beta sub 1 or b sub 1 is the slope of the regression line, and then knowing the slope, we can calculate the correlation coefficient, which is a standardized slope. It's the slope times the standard deviation of x divided by the standard deviation of the y variable. So here's an example printout from running this. This is done in Stata, but any statistical program you use will have a output that looks something like this. So first well, maybe not necessarily first, but one of the first things we want to look at is our R-squared value. And you can see that it's actually pretty good. So what this means is that 70% of the variability in cholesterol is explained by age, which in medical research is really good. But and then there's an adjusted R-squared that adjusts for sample size. So in this case, if you have a small sample size, it's going to be a little bit less than that. And so in the first thing we have here is what we call our source table. And so here's our sum of squares, what we call the degrees of freedom. The mean square is just the sum of squares divided by the degrees of freedom. And so you can see here that if we divide our model sum of squares, this is our regression sum of squares, 101,000 by the total sum of squares, which is the sum of these two, we get the R-squared value, in this case, 0.7. And so in the information here that's tells us the regression coefficient, which in this case is 5.3. And so what this means is that for every year increase in age, cholesterol increases by 5.3 units. And in terms of our intercept term here, 102.57, what that means is that when age is 0, the cholesterol level is 102, plus or minus a little bit. Well, if you think about this, an age of 0 is not very meaningful unless we're talking about newborns. But in this case, what we do, or what is often done, is that we will center age on a particular value. And so sometimes what's done is that we center age. In this case, we center it on 40. And maybe you might pick the mean age of your sample, or some quantile. But anyway, so here I've calculated a new variable, and it's the individual's age minus 40. So if that value is 0, that means that we have a patient with age 40. If their age is 45, then the centered age is going to be +5. If their age is 35, then it's going to be a -5. And so you can see now that when we do our regression with age centered at 40, we get everything is the same except the intercept, or the constant. And so in this case, what this tells us that when age is 40, the cholesterol level is 315. But we have the same the R-squared. Let me go back one. We have the same, essentially the same R-squared, or we do have the same R-squared. The sums of squares are the same, even though we have changed our age scale from 0 to whatever to plus or minus 40. Okay. So in terms of graphics or illustrating this, here is our plot of observed values in our regression line overlaid on top of it. And so in this case, our regression looks pretty good. It certainly isn't. We could easily define the relationship between age and cholesterol as a linear relationship. And as we saw, the R squared was 70%. So we have a really pretty good fit to our data. And so what is typically done when we plot the data is we include confidence intervals. And so this is the plot of the regression with 95% confidence intervals. And what the confidence interval means is that if we were to do this over and over again, 95% of the time of all the runs that we did, that 95 times out of 100, the regression line would fall within these bounds. And you can see when we plot the confidence interval that it's really good at the mean age. As you get to the extremes of age, the confidence interval gets somewhat wider. And this is true of all regression lines. So if you see a regression presented in a paper and they have straight lines there from lowest to highest, you know that either they have done the confidence intervals wrong or they're doing something different. But you will always see those curved confidence intervals with the regression line. So what we want to do is make sure that our regression model is valid. And so we're going to do some regression diagnostics. Sometimes you'll see this presented in papers, but most often you don't. But the probably the main one that we want to do is what's called a residual analysis. And remember that residuals were the difference between the observed value and the predicted or the regressed value. And so these residuals, the predicted minus the observed, should be randomly distributed, or they should have a mean of 0 and be normally distributed. And they should also have a random distribution about the independent variables. So we'll look at a couple examples here. And so what we want to look for in our plot or in our data, and there's a way of doing this, most statistical programs can identify these for you, are what we call outliers and influential data points. And just to point out that an outlier is not necessarily an influential data point. It can be, but it may not be. But if we have an influential data point, what that means is that it's going to change the regression coefficients, statistically speaking, or there's going to be a significant change in the regression coefficients. So if we look at our residuals, take our predicted minus observed, and we plot that against a normal distribution with mean of 0, then this is hopefully what we should get. So the straight line, if all the points, which is a plot of the residuals against the normal distribution, should fall on that straight line. Now, in this case, they don't, and obviously there are never any, real data that you analyze. Is not every point's going to fall on that line. But if you're what we call QQ plot or Q normal plot looks like this, this is really pretty good. So we would say that we don't really have any kind of problem with the normal distribution of residuals. In the same way, if we look at a plot of the residuals against the predicted values, then we should see something like this. In other words, they would have a mean of 0 and they would be randomly scattered. And usually what we look at is plus or minus 2 standard deviations from the mean of 0. And then if we also can plot them against values of the variables, our independent variables, so in this case, age, again, we see that we should get a mean, the mean of the residuals should be 0, and we should get more or less random scatter about the mean of 0 if we plot the residuals against each age. On the other hand, if you do that and you get a plot that looks something like this, then we're kind of in trouble a little bit, because that means that we have an issue with variability, and that in this case, you can see with a younger age, the residuals are, pretty good as far as being distributed about 0 residual mean. But as age increases, the residuals increase, and they increase quite dramatically. So in this case, we'd have to go back and do something to adjust for this or take care of this. So those are the some of the tests that we want to do in looking at how valid our, or how good our regression is in addition to the R-squared value. So let me then take a look at a multivariable analysis where we have more than one independent variable. And so I've added weight to our data set here. And so what we want to do is we want to regress age and weight, or regress cholesterol on weight and age. And so our multiple linear regression, which is usually abbreviated MLR, will look like this, where we have multiple independent variables. Again, the beta or B sub 0 is the intercept. And now the regression coefficients, in this case, the B sub 1, B sub 2, what they represent is the rate of change in the outcome Y for every unit increase or decrease in the independent variables, adjusted for all other independent variables in the model. So in this case, if we have cholesterol, we're going to look at it as a function of age and weight. Then the regression coefficient B sub 1 of age is adjusted for weight, and the regression coefficient B sub 2 for weight is adjusted for age. So the interpretation is still the same as far as rate of change, except that now it's been adjusted for all the however many variables you have in the model. And so here's the output from looking at age and weight in combination as far as being associated or predicting cholesterol. And so again, you see that we have our regression coefficient for age. And you remember from when we just did age by itself, it was 5.3. So it hasn't changed much. And so when we look at that, we think, well, weight really hasn't added much to our regression equation here. And you can see that we still get, or I'll point out here first, that the regression coefficient is not statistically significant. In other words, the p-value is 0.573, much larger than the traditional 0.05. And we can see that in the 95% confidence interval, where the range is minus 1.1 to 1.9. And so if the confidence interval includes 0 in linear regression, that means that the variable is not contributing much to the regression equation. And we can see that in the R square that it's pretty much the same. It hasn't changed that much from just age by itself. And so there's a couple things we could do. One is that if we were looking at a prediction equation here for cholesterol, we don't really need weight. Age would be sufficient all by itself, so we could drop weight out of the equation. Okay, so the next thing we want to look at is the interactions of when we have more than one independent variable in our equation. And so what an interaction means is that the effects of one independent variable are not the same across levels of another independent variable. So our terminology here, when we talk about a significant main effect with no interaction, or if there's no interaction, significant interaction, then we can interpret the main effect directly. Two types of interactions can occur, what we call an ordinal interaction and a disordinal interaction, and this gives an example. So if we say we're comparing two groups here on some with respect to some outcome, and so there's a main effect, but there's no interaction, then we'll get parallel lines. An ordinal interaction means that they were sort of similar, but then were different at another point in the measurement. In disordinal, then we have they started at different points and they ended up at different points in from our regression equation. So let me illustrate this, and at the same time, let me illustrate hypothesis testing using linear regression. And so what we are interested in here is comparing two drugs in the reduction of diastolic blood pressure. And so I have some data here, the diastolic blood pressure for each individual, the drug that they were on, their age, and their sex. Now, in this case, my design is what's called a non-randomized comparative effectiveness. In other words, patients have not been randomly assigned to the drug condition. And so in terms of our statistical presentation of this, or our statistical jargon, if you want, our research hypothesis is that there's a difference between drug A and B with respect to reducing blood pressure. And say in this case, we hope that we're looking for drug A to be better, so we've coded that 1 and drug B is 0. Our null hypothesis, statistically speaking, is that there's no difference between A and B with respect to reducing blood pressure. So because the study in this case is non-randomized, there's potential for selection bias with respect to the treatment drug. Now, if the study had been randomized, then we could just do a simple t-test comparing A and B. We wouldn't have to worry about any potential confounders. But in this case, since they weren't randomized, then we might have another explanation for the difference between the two drugs, if there is one. And so in this case, would one set of patients be older than the other ones, or would there be a difference in the distribution of sex? Typically, when you have this non-randomized kind of design, age, sex, and race are usually the variables that are included to control for differences that might or possibilities that might explain the difference between the drug outcomes. And so in this case, what we're going to do is our regression model is going to be drug plus age plus sex, and those are what we call the main effects. And then we have two interactions, drug by age and drug by sex. And so the first thing that we should do, although maybe people don't do it, but look at the distribution of sex and age in our two drug conditions. And so we can see that there's almost there's an opposite reversal between males and females in the two drug groups. But even more important than that, if we look at the mean age in both groups, we can see that we may have real problems here, because the patients in Group B are on average 8 years older than the ones in Group A. So we've got a real potential confounder there as far as our results are concerned. And so here's our output from including, well, I've dropped out the drug by sex because that was not statistically significant. So you can see that what I have is a significant interaction between drug and age. And so that means that the effect of the drugs of A and B is not the same across ages. We also have a significant main effect for sex and for drug, but because the interaction is statistically significant, we have to interpret that interaction. And so one way we can do this is we can compare the observed blood pressures for the two groups and look at the adjusted blood pressures for the combination of drugs and sex and age. And so we can see that there's some difference here, both between males and females, and there's a difference over age. So for example, females in drug A group at age 50, the blood pressure is 67, but at age 70, it's 72. For males, on the other hand, you can see that the difference is not so great at age 50 and at age 70. And so the best way to see this is to plot the predicted values or the adjusted values for the combinations of drug, sex, and age. Or in this case, since age is continuous, we'll plot the change in diastolic blood pressure over age. And so you can obviously see here the interaction that for drug B, there's still a difference between males and females, but the change is, there's actually no change over age. It's essentially the same from the youngest age to the oldest age. On the other hand, for drug A, we see that there is a change over age with change with increasing age, and we still see that females are doing better than males because they have generally lower pressure, but both are increasing as age increases in drug A. And so we are going to have somewhat of a dilemma in interpreting our results, that we're not going to just be able to straightforwardly say that drug A is better than drug B. Okay, then I want to talk just a little bit about mixed effects models. And what we mean by that is that we have two different kinds of effects. We have fixed effects. Those are effects that are attributable to a finite set of levels of factor like in our last example treatment, say drug treatment, sex, race, age might be fixed effects. Random effects, however, we have an infinite set of levels of a factor of which only a random sample appear in the data. And examples of this are like clinical trial sites or geographic regions, where those might influence our results if we have patients coming from different sites or different geographic regions. Just a couple of points here. Patients or subjects, they're always considered a random effect, even if the study is non-randomized. Then if we have like study sites or geographic regions or some other random effect there, we refer to that as hierarchical or clustered. In other words, we have patients, a set of patients coming from one study site, a set of patients coming from another one. And so the question is, does the different sites affect our outcome? Another mixed effects is where we have repeated measures, where we have observations repeated over time for each subject. And generally, when we analyze the change over time, we look at time as a fixed effect. And then the term variance component, I just point that out if you happen to see that. What that is the variance of a random effect. So let me give an example here from our COURAGE trial that we did some years ago, where we have 3 different healthcare systems, US, Canada, and VA. And then within each healthcare system, there are different sites. Now, there aren't just 2 sites at each one, but and then within each site, patients are randomized to either PCI, percutaneous coronary intervention, or OMT, optimal medical therapy. And so we have a hierarchical structure here where we're going to treat healthcare systems as a random effects, because these are just 3 healthcare systems out of many. And the same thing for sites. We have different sites. And so those would be considered random effects. The fixed effect is whether they were randomized to PCI or OMT. And then we're going to follow them up over time as well. So our model here is the Seattle Angina Questionnaire, the SAQ or the SAC. It is modeled as a function of therapy, whether it's PCI or OMT plus follow-up time, and then our random effect, where we have random effects for patients, which is usually represented by I, J is the sites, and K, the healthcare systems. And then, as I say, U is the random effect of patients within sites within healthcare systems. And so just to show the results here in terms of plotting the mean values for different domains of the Seattle Angina Questionnaire, physical limitation, angina stability and frequency, and quality of life. And so you can see that what we have here is actually a nonlinear trends for both, where we have kind of a sharp increase early on, and then it more or less levels out. And you can see that the PCI component or group is doing better until we get further out in time, and then there becomes less and less difference between the 2 groups. So one other application here that I want to go over, hopefully fairly quickly as I'm running out of time, is what we call multivariate analysis of variance, or you may have heard the term MANOVA. The cool thing, I guess, from doing multivariate analysis, although you can do different things, is what we call profile analysis. And so in my example here, I have two groups of valve repair, microvalve surgery, microvalve repair versus microvalve replacement. And what the investigators were interested in doing was to compare the SF-36. Now, the SF-36, as many quality of life instruments have, are different domains. And so the SF-36 has 8 domains, or at least the early version did, like physical function and so on. And so what we're going to do is we're going to compare the profile, not just the individual domains. And so the first thing, of course, we'll do is we'll test for a profile by group interaction. And if that's not significant, then we can interpret the group main effects as the difference between profiles, not just one of the domains. And so this is the old SF-36 components, physical function, role physical, and so on, and mental health, emotional, social functions, and so on. And so what we want to do is we want to model the profile here as a function of a valve replacement procedure, in this case, plus follow-up time and plus the interaction of time, and then we have our random variance for individuals. And you can see that the right side of the equation is similar to what we've looked at before. However, the left side of the equation, instead of having a single variable here, what I have is a matrix of the 8 components of the SF-36. And so that's what we're going to test, is the SF-36 as a whole, as a profile. Is that different between microvalve repair or replacement? And if we plot this, this is what the results turned out to be. And so you can see that in terms of profile, the repair group is basically doing better at baseline, and they're also doing better 1 year post-surgery. However, at 4 or more years post-surgery, you can see that that they're virtually identical, that there's no difference between the profiles. And so doing profile analysis is sometimes useful in looking at not only differences at the entire profile of an instrument, but also looking at whether it changes over time. Okay, then I want to, let's see, I think I have a couple more things here. What if the relationship between the outcome and the covariates or the independent variables is nonlinear? Well, there's different solutions that we can, linear solutions that we can apply. And what we mean by that is that they are linear in the parameters, in other words, in the regression coefficients. And so I've listed 3 common ones that we can do here. Polynomial regression, which is using an integer polynomial, fractional polynomial regression, and then splines or piecewise regression. Now, if you actually wanted to do what I termed here as a real nonlinear model, then you're going to have to do something a lot more complicated, where we have functions that are nonlinear in the parameters, but that's for another day. And so here's an example. So integer polynomials, what we're going to do is we're going to raise 1 or more of the independent variables to an integer power. And so here in our first one, we were going to raise age to the 2nd power. And so we might get, if this turns out to be significant, we would get some sort of nonlinear relationship between age and cholesterol. Fractional polynomials are just that. They're fractions rather than an integer. And so, for example, maybe we'll raise age to the 2.25 power. And then piecewise regression, I've just illustrated that with a picture here. But the basic question that we'll have to answer in this is where are the change points. But you can see that we have 3 different linear components of this relationship that we could model. And so here's some examples. This one in the upper left I've shown before, where if we did a linear model, we get a coefficient of 0, but clearly there is some relationship. At the bottom left here, we have 2 different models. We have the linear model, where we just have the intercept and the slope. And you can see that this doesn't fit the data very well. But if we introduce a square term to the x variable, then we get a much better fit to the data. And then in the right-hand side here, this is actually taken from a published article where they modeled this as linear. But the question would be, would this better be modeled as nonlinear? Because you can kind of see here that in the lower values here, there's kind of a almost a straight line relationship, where somewhere in here between 4 and 5, there's a much bigger increase. So maybe that would be better modeled as nonlinear. Okay, and then the final topic I want to talk about is regression discontinuity. And basically, this is looking at data that's collected over a period of time with an intervention, some kind of intervention occurring at some point in time. And so what we're basically going to do is we're going to develop a regression model before the intervention and a model after the intervention and compare the 2 regressions to see whether they're the same. Now, if both pre and post are linear, then it's really easy, because all we have to do is basically use a t-test to compare the slopes or the regression coefficients and the intercepts. And so this is what a regression discontinuity would look like, where our intervention here is represented by X, and then we have a linear regression model pre, and then another one post. And so we can see that they'd obviously be different here because they have differing slopes. And then just to illustrate different situations, on the left-hand side here, we can see that after the intervention, there's a negative slope. So they're comparing the slopes would tell us whether those are different or not. On the far right, we have a situation where the slopes aren't different pre and post, but the intercepts are. In other words, there's a big drop in the average value after the intervention. In the middle one, what would we say about this? Well, you can see that in this case, we'd have to conclude there's no impact of the intervention, because the outcome was decreasing pre-intervention, and it's decreasing at the same rate post-intervention. Okay, let me close then with these comments, and then if we have a couple minutes here for questions. So linear regression is what we call a robust analysis. What that means is it's still valid if assumptions are violated. For example, the most common one being non-normality. If our outcome data isn't exactly normal, or maybe it's even skewed somewhat, our linear regression is still pretty robust to giving us valid results. Now, obviously, there's a point at which this isn't true anymore. If you get extreme non-normality, for example, or your plot of residuals shows a very extreme non-normally distributed residuals, then obviously linear regression isn't valid, and we'll have to maybe do something else to adjust for that. Now, one thing that's commonly done is to take like a log transform of the outcome variable to make it more normally distributed, although that doesn't always work either. And then if we're doing multiple linear regression, sort of the rule of thumb is that you need 10 to 20 subjects or patients per variable in the equation. So if you have, say, 5 variables in there, then you should have at least 50, but 100 subjects would be even better. And just to add to that, the sample and kind of depending on the reason you're doing regression might also depend on the effect size. In other words, how big of a difference do you want to see between, say, treatment groups, or how big do you want to see the betas in your regression equation? And then finally, what I think is kind of common knowledge, or I'm sure heard before, is that the correlation or association doesn't necessarily mean causation. In other words, we can't say that age causes cholesterol increases. We say there's this association, and maybe it's a strong association, but it's not age itself isn't necessarily the cause. So with that, I will stop. And well, not quite. So there is one textbook that I think is really good on regression modeling, and that's the reference by Harrell. That was published back in 2015. It's the second edition. It's really good. It's readable, and it has a lot of computer syntax in there in R language that shows you actually, from a practical standpoint, how to set up different models. And he does both linear models, logistic, and time to event regression models or survival analysis. We'll actually look at these in the next 2 sessions, logistic next month, and then the month after that, survival analysis. So with that, I will stop, and let me see if there are any questions. Which I think, yeah, if there's any questions, I think we use the Q&A. I know we're right at 1, so if you do have any questions, please feel free to email me, or if you have some data that you're actually interested in analyzing, also email me, and we can set that up. Okay, all right. Well, I thank you for your time, and we will meet again next month.